K. Paranivelu, Professor at the Center for Environmental Studies and Director of Center for Climate Change and Disaster Management, Anna University, Chennai. He obtained his PhD degree from Indian Institute of Technology, Madras, Chennai. He worked as project officer for a brief period at IIT Madras and moved on to the Center for Environmental Studies, Anna University in 1992. He was a visiting professor at Chungam National University, South Korea during 2007. He has been teaching courses on environmental chemistry, environmental pollution control, and instrumental methods of analysis since last 27 years. He has guided 75 students for ME and MSc, 4 MPhil, 2 MS, and 15 PhDs. He has published 135 papers in journals and 90 in conference and symposiums. He has received several awards in national and international levels.
Welcome to the lecture series on the chemistry of environment. We are discussing about fundamentals of chemistry, and today we are going to discuss about radioactivity. Radioactivity and radioisotopes also one of the important component of environment. And first we will see what is radioisotopes and what are the speciality about it, what are the applications of this radioisotopes we will see. Usually nucleus of an atom is composed of both protons and neutrons, and except hydrogen 1, other things are composed of both protons and neutrons, all elements. And the number of protons in the nucleus is usually called atomic number, represented by Z of the particular element, and the sum of the number of protons and neutrons is normally known as mass number, represented by capital A. Okay. And atoms of the same atomic number, whereas with a different mass number, are usually known as isotopes of the element. For example, in hydrogen itself we have hydrogen 1, hydrogen deuterium, and hydrogen 3 tritium. So, there are 3 isotopes in hydrogen itself. And if you look at carbon, we have carbon 12, 13, 14 isotopes. So, like this there are many radioisotopes are available in nature, as well as it is all produced artificially. When referring to a single type of nucleus, we often use the term what is called nuclide, and represented by X of the particular element, and Z is the atomic number, and A is the mass number of the particular element. And for example, we call it as carbon 14 with the atomic number 6 and mass number 14, we call it as carbon 14 isotope. So, like this there are many elements are available. And when we consider a radioactive isotope of a particular element, normally it is defined as an atom that contain usually an unstable combination of neutron and protons. Okay. Whenever the ratio is close to 1, that particular element will be stable, and suppose the proton neutron ratio differs from 1, then there is a possibility of that particular isotope will be radioactive and emit radiations. Okay. So, unstable combination of neutron and protons is a reason for this, and in this situation an excess energy in the nucleus, and this particular radioactive isotope will emit radiations during the decay to a particular stable form of it. Okay. And radioactive isotopes, whatever the rays they emit, have many useful applications in day to day life, especially in medicine. For example, cobalt-60 isotope is one of the very extensively employed as a radiation source to arrest the development of cancer in human beings. So, this is cobalt-60 is one of the very important isotope. And similarly, other radioactive isotopes are also used as a tracer for diagnostic purposes in medical field, especially to follow research on metabolic process. These radioactive isotopes find a lot of nuclear related medicine application. Even other field as well, for example, to find out where is the oil leak, these radioactive isotopes are used as a tracer. So, like this there are many applications of this radioactive isotopes in day to day life. And For example, some of these radioactive isotopes are, and their half-life period: hydrogen with the 3 hydrogen isotope 3 tritium, it has a half-life period is at 12.43 years. And if you consider carbon 14, this is the half-life period is very high, 5,700 years. And if you consider chlorine 36, this is very, very high, 3 lakhs plus years is a half-life period. That means the half of the amount of original activity to reduce the half of it is normally known as half-life period or T half. And radioactive isotope, they have different charges. For example, a radioactive substance is emitting, they may emit alpha, beta, gamma rays like this, and whatever it is from a particular radioactive isotope, normally put it in a lead block, that it will emit through the small hole different rays. And if you put a electrically charged plate, that is anode and cathode, and depending on the charge of this radioactive particles, they will be deflected appropriately. For example, alpha rays will be attracted towards a negatively charged electrode and beta rays towards the positively charged. Gamma rays will go as such, and accordingly we can find what is the charge on this radioactive particles. For example, alpha particle represented by helium nucleus with 2 protons and mass number 4, helium, that is the alpha particle, and this is one of the high energy nuclei. Similarly, beta particle with a negative charge, and this is again high energy electron, and positron with a positive charge opposite of the electron. Positive charge here, that is particle with the same mass of an electron but with 1 unit of positive charge. Instead of negative, it is positive charge. Similarly, proton is possible, and neutron, gamma rays, in which it is a mere radioactive, very high energy electromagnetic radiations. So, like this, there are possibility of different nuclear particles will emit from the because of the isotopes emission. And the radioactivity is usually measured in terms of becquerel or curie, that is a old unit. Curie is a old unit, the current unit is becquerel, shortly BQ, and this is equivalent to 1 disintegration per second, that is a DPS. And earlier it was measured in Curie because it was Madame Marie Curie who invented this radioactivity. And for example, 1 gram of radium 226, that is it will be equivalent to 1 Curie, that is actually 3.7 into 10 power 10 radioactivity decay per second. And so, becquerel is 1 decay per second, whereas Curie is the same equivalent as 3.7 into 10 power 10 decays per second. And these radioactivity is also measured in water. Drinking water, radioactive particle emission should not be very high. For example, if it is an alpha emitter and maximum allowable permissible limit is 0.1 becquerel per liter. Similarly, suppose any beta emitting radioactive particles are present in drinking water, the maximum allowable concentration is 1 becquerel per liter. These radioactive instruments are routinely measured with what is called GM counter or Gehel-Muller counter to measure the radioactivity, and this GM counter is available in a portable or handheld form. We can take it to the field in a portable form and measure the radioactivity. And this is one of the common choice of radioactivity measurement or detector normally available in a laboratory. And this GM counter can detect alpha, beta and gamma rays, and usually if the radioactivity is from medium to high energy range, for example, a beta containing phosphorus 32 as phosphorus 33, chlorine 36, calcium 45, etc. are beta emitters with a medium to high energy. Definitely it is possible to measure with GM counter by ionization of this radioactivity, that is of the inert gas put into this radioactive source, it will be ionized and that will be moved to the appropriate electrode and the count is measured. But this GM counter is not suitable for detecting very low energy beta emitters, for example, hydrogen 3, carbon 14, sulfur 35 and a low energy gamma emitters like iodine 125 or iodine 131 cannot be measured if the activity is very low, whether it is alpha or beta or gamma, whatever it is, GM counter is not possible. In such cases, we have to go for what is called another laboratory based instrument, what is called liquid scintillation counter, LSC, popularly called LSC. This is a fixed instrument and this can be used for measuring low radioactive emitting materials. For detecting low energy beta emitters such as hydrogen 3, which has an energy of 19 kilowatts, very low, carbon 14 or sulfur 35 with the 167 kilowatts of energy, these type of low emitting things can be measured easily with the liquid scintillation counter, in which either sodium iodide or organic solvent can be used as a liquid in which the radioactive materials will come and interact with this, and there are photomultiplier tubes PMT which can be used to measure the radiations emitted from this. In this radioisotope, what is important is energy related to this radioisotope is very important. One term is called what is binding energy, that is energy needed to break the nucleus into its constituent proton and neutron. What is the energy required is known by binding energy, and binding energy per nucleon, that is energy needed to remove a nucleon from a nucleus. This is normally known as binding energy per nucleon. And related to this, mass defect or mass difference is also very important, that is difference between the mass of a nucleus and the total mass of its constituent nucleus, namely proton and neutron. And this mass defect is very important to know what are the energy emitted during nuclear fission or fusion. And the mass defect is nothing but the difference between the mass of the proton, mass of the nucleus and neutron and mass of the nucleus. That difference is normally known as mass defect, and the nucleus is consisting of both proton and neutron, and actually if you calculate the individual proton mass and individual neutron mass, there will be a difference. This difference is normally known as mass defect, and this mass as per the Einstein popular equation is equivalent to mc square. That is whatever the mass difference here is converted into energy and emitted during the process. The popular equation is equivalent to m, that is the mass of the particular one employed in this, and c is the velocity constant of light, and if we multiply we will get what are the energy released in a process. And nuclear changes occur usually with a simultaneous release of energy during the nuclear change, and based on this and using the Einstein equation we can find out what is the amount of energy that actually results when matter is converted into energy, that is E is equivalent to mc square. The potential power locked inside a uranium atom is not very small. It is very huge quantity of energy is stored inside the uranium. For example, if you take 1 kilogram of the coal and burn it, and we get the energy out as not usually around 8 kilowatts or 8 units of heat will be generated. Whereas if you take 1 kilogram of uranium 235 and we create a burn it, and suppose we create energy, that will be equivalent to very huge amount of energy will be released by burning 1 kilogram of uranium, and this is actually equivalent to 2 to 3 million tons million times more than the energy released by burning 1 kilogram of the coal itself. and the fission of 1 gram of uranium or plutonium, radioactive plutonium per day liberates about 1 million watts of energy, and this is the energy equivalent to 3 tons of coal or about 600 gallons of fuel oil per day is burned. Okay. That is a huge quantity, 3 tons or 600 gallons of fuel. If you burn it, that energy is equivalent to 1 gram of uranium is burnt in the nuclear process. So, huge amount of energy is released during the burning of radioactive material as per the Einstein equation, and this actually, if you consider with the coal or fuel, any other fuel used, fossil fuel, and huge quantity of carbon dioxide will also be eliminated, emitted simultaneously, and that is put into the atmosphere. That is mainly responsible for the global warming and the consequent climate change, and this is avoided. Suppose we go for small quantity of uranium, huge quantity of carbon dioxide we can cut short, that is actually going into the atmosphere. And to better to understand the mass defect, just consider the plutonium 239, and suppose we assume, and this is reacted with a neutron, this is a mass number, plutonium mass number, and this will be a fish, and we will get gold and phosphorus 31 plus 5 neutrons also will be released, and these are the 3 products. Suppose we plutonium is reacted with a neutron, and if you leave the mass of the reactants, that is plutonium 239.0552, and for neutron this is, so total masses comes to 240.0609 gram, and if we analyze the mass of the products here, that is actually 203.9 for gold and 30.97 for phosphorus and 5 neutron mass, and the total mass is this, and this we see there is a difference. The difference or change in mass is equivalent to minus 0.0659 gram, and this is called mass defect, and this is what converted into energy during the burning of nuclear fuels. And using this mass in the Einstein equation, we put it this mass into velocity of light, we will get so many, that is 6 trillion joules of energy is given out during this process. And radioactive isotopes follow the first order kinetics, and they can be predicted based on the decay rate of the first order, that is normally lambda n, and the half life T of is equivalent to ln 2 by lambda again, and equivalent to 0.693, and normally in the kinetics we will write small k for the rate constant, whereas here it is represented by this unit, and usually the half life period first order kinetics, it can be shown like this. And concerned with the mass defect, what is important is we can generate huge energy using this radioactive isotopes. That is the basis of nuclear reactor, that is an apparatus designed to carefully control the progress of nuclear reaction and extract the resulting energy for useful purpose. This is called nuclear reactor, and there are 2 types of reactors. One is based on fission, the other one is fusion of lighter nuclei to form a bigger one and release energy. In the fission of a larger nuclei, for example, uranium 235 is bombarded with neutron, it is split into barium ion with the 139 and krypton 94 plus 3 neutrons also released plus along with the energy. This energy, as we discussed, is huge quantity. So, these neutron can themselves simulate other trans uranium material, that is uranium nuclei, to undergo further fission. So, each one of this create 1 neutron, another 3 neutron. So, this process is usually called chain reaction, that is a single neutron initially reacts, well multiply initially 3 and this in further 3 like this. So, this is called a chain reaction, but in a nuclear reactor we should have a controlled one or a moderator to control this reaction process. The other way we can generate nuclear energy is through fusion. And here the process involves fusion of smaller nuclei when they are combined into larger nuclei. Similarly, here also huge quantity of energy is released. And for example, 4 hydrogen atom as combined, it will form helium plus huge amount of energy is also released in this process. And here the amount of energy given off per mole of reactant is only 1/10 of the amount of the fission reaction in terms of mole per mole, 1/10 only we will get. But in terms of we go for actual absolute mass and a mass that is per gram basis, hydrogen fusion gives off 10 times more energy than fission reaction energy amount. So, this way this is more advantageous. And also we can notice here the fusion reaction, we get a product of helium which is not usually a isotope range of material. Whereas, if we consider fission reaction, mostly the products are radioactive ones. That means, they will further emit any one of these particles, namely alpha, beta or gamma rays. So, fusion has some advantages here. But the problem is, especially for environmentalists, the residue of the nuclear reactor, namely with the help of fission or fusion reaction, the waste disposal of this radioactive waste is a huge worry, because they contain radioactive isotope alpha, beta, gamma rays, whatever it is, either uranium or thorium is used for generating energy. Ultimately, they end up with radioactive material. Sometimes it may be low or medium or high level waste as possible. So, these waste has to be taken care, stored separately in a appropriate way. And some of this possible ways are ground disposal, or geological disposal, above ground disposal or geological disposal, deep borehole disposal, and disposal at a subterranean zone. And this is especially there is a risk of earthquake, seismic activities there, definitely a plate movement will be there. This is create another problem. Also, the radioactive waste may be dumped into the ocean. Earlier it was done, but it is declared as illegal by international treaty. Now, even ocean underground, it should be taken care of in a specialized way after vitrification or solidification of the radioactive waste, so that it is not exposed. And disposal in outer space also is possible, but very costly and high risk of space vehicle failure also when they are exposed to huge amount of radiation. But the possibility is, whatever it is, the mode of disposal should be, it should be the radioactive material should be vitrified or solidified in a strong form that is heating at a very high temperature, so that it is safely fixed, and then the fixed material may be buried in a appropriate place. So, apart from this energy generation, the radioactive materials also finds lot of analytical scope. That is, the radioactive materials alpha, beta, gamma rays may be made to use for monitoring environmental pollutants also. So, some of the methods are neutron activation analysis. This is one of the very popular method and serves as any dispute is there as a standard method of measuring. So, here ordinary material is activated by bombarding with a neutron generated through radioactive source or cyclotron, whatever it is. The neutron is made to react and make the non-active material in terms of radioactivity to or induce radioactivity by bombarding with a neutron, and ultimately they will emit, depending on the half life period, different isotopes will emit different things, and that can be used for measurement of radioactivity, because each isotope it will emit energy at a particular energy level, and that can be used to measure that is both qualitative as well as quantitative analysis is possible using this neutron activation analysis, and this analysis serves as a standard method, not routinely used. Whenever there is a dispute with the other analytical method, this is a method of choice and the results are undisturbed. The court has to agree to this result of this, but this method is a somewhat a slow process. Other method is beta attenuation for air pollutant, especially particulate matter. Particulate matter with a 10 and 2.5 can be measured continuously using this beta array attenuation method. That is a clean tap there and which the beta array may not be attenuated. Once particulate matter is accumulated on the clean filtered tube, what happens is the dust particle either 10 with the appropriate PM head selection, either 10 or 2.5, they allow the particular dust alone, and that can be used to measure what is the amount of particulate matter continuously using this beta array attenuation method with a PMT detector. Also, in the gas chromatography, mostly used for estimation of organic pollutants like chlorinated pesticide, etc., we can use for GC with the electron capture detector. Even in the electron capture detector, the source contains radioactive materials like cobalt 60 or nickel. Radioactive isotope are employed in this electron capture. That means they will release beta rays. Any pollutant comes like chlorinated pesticide, chlorinated or organic compounds in general, they pick up this electron, comes from the radioactive source and causes conductivity differently, or the measuring things differently. So, this is also used for thing. So, the nuclear based analytical method also popular for environmental monitoring, like chlorinated organics including pesticide, chlorinated pesticide, particulate matter in air, and whatever the material, especially solid material liquid, can be analyzed using neutron activation analysis also. So, to sum up, nuclear energy comes from tiny mass change and nuclei as a radioactive process occur. As I told you, mass defect is very small maybe, but the amount of energy released is huge quantity, okay, and that is what makes this a good choice. In fission reaction, large nuclei break apart and releases energy, whereas in fusion, that is a small nuclei merge together and release energy, and the quantum is very huge. Even nuclear fusion is taking place in the solar part also. The close to sun, the fusion is taking place, and that also release lot of amount of energy. So, both fission and fusion is one considered as a source of producing electricity energy. And if we compare this energy in terms of chemical combustion of coal or oil, where in which the order of energy released is in hundreds kilojoules per mole, whereas if we consider nuclear reaction, the amount of energy given off by burning uranium 35 or thorium or plutonium, etc., the energy given off as huge quantity, that is billions of kilojoules of energy per mole is liberated by through this fission or fusion of lighter molecule. And very importantly, what happens is there is no emission of carbon dioxide. This is what very important for this in this nuclear reaction, whereas in chemical combustion with the coal or oil, huge quantity of carbon dioxide is there. Here no emission of carbon dioxide, that means it is climate friendly. Thank you.